So, hi, my name is Tomáš, and I'm here to talk about Postgres and data corruption. Who here actually is using Postgres in okay, cool. Who's using like other databases like MySQL and so on? Okay, leave. No, really. I mean, I do work for a company which is called Second Quadrant. We do all kinds of Postgres-related stuff, including contributions to Postgres. I myself am a long-term contributor and committer. And I'm here actually to talk about a topic which is kind of sad and depressing, and that's data corruption, which is not just about Postgres, but it's about all databases. Even if you use like Oracle, MySQL, whatever, you will face the issue of data corruption, right? So this talk has exactly 0% of Python code. So if you came here to PyCon expecting talks about Python, this is not one of them, right? So I've been asked to submit to give you like a bit of variety here. So this is a very different type of talk. I'm actually working on Postgres. I do work on just Postgres. This topic is about all databases in general, right? So I will give you some examples of data corruption issues in Postgres that you can actually run into. But other databases have similar issues to some extent, right? You might actually know that Postgres, since like a year ago or maybe 2 years ago, has a feature which is called data checksums, which means like checksumming the data files. And this talk is explaining like why that's not actually a complete solution to data corruption, right? So at the end, I will talk a bit about data checksums and why it actually doesn't solve various types of data corruption that you can run into in production. So it's not the solution, right? So what actually is a data corruption? Right? I mean, like, what's the definition? In a very narrow definition, you could say that it's the situation when the storage returns incorrect data, right? But that's really very specific case of data corruption. A much more plausible definition is that it's simply a state when the database has data in unexpected state, right? I mean, like, it could be logical data corruption when you have like mismatching indexes and data and tables. It could be something when you can't even read the data from disk. It could be something in between, like random bit flips, which changes the data on disk, but the database is unaware of that, and so on. By the way, if you have questions during the talk, please don't wait until the end. Just shout, and I will try to answer them right away, right? So really, I will use this much wider definition of data corruption because that's effectively what matters for the application, right? I mean, like, the application expects some state from the database to be in like a consistent state. And when that's violated, it's kind of an issue, right? So it's unexpected state of data. And the truth is that the older and larger your database is, the more likely it's already corrupted, right? So you kind of have to accept the fact that your database is corrupted already, and you need to act defensively to kind of limit the damage, right? This is especially true when, for example, the database was created like 10 years ago and went through multiple versions of Postgres updated over the years. It could be minor upgrades, it could be like binary compatible, it could be major upgrades from, say, Postgres 9.3 to 9.5 or something like that, which may actually require, during the process of upgrade, modifying the data files or something like that. But if you have a data corruption which happened like 10 years ago, it might still be there, right? You just don't know that yet. But I mean, like, don't panic, right? I mean, like, that's life. You can't really solve this by using any other database because all databases kind of have this issue. And Postgres is still very, very reliable database. I mean, like, we pay close attention to all data corruption issues. So if you run into a data corruption issue and you don't know what caused that, please report that to the mailing list and we will try to help you, because we don't like the situation when people lose data, because we are also using the Postgres for our life and we could be affected by that as well, right? So Postgres is still very reliable, but let's talk about like the data corruption in general. So I have already mentioned like what is data corruption, the very very broad definition. Next, I will talk about sources of data corruption. Like, where does data corruption come from? Like, if you have a database, how could it get corrupted in some way? I will give you some examples from the history of Postgres. Some of those issues are already solved, but some of them are not, and you may actually be affected by them. And finally, we will talk about like what steps you can take to actually minimize the likelihood or the damage caused by data corruption. So first of all, data corruption has many, many different sources, right? I mean, like, if you imagine the stack your database is running on, it's from the hardware to maybe some storage appliance like NAS or SAN or whatever. Then you have the operating system on the host where the database is running. Then you have the database. And finally, you have the application. And each of those layers in the stack can actually cause data corruption. Different types of data corruption, but the data corruption nevertheless. So the most common case of data corruption is at the storage level, right? I mean, like, you have storage devices, disks, or network-attached storage, and those things can do really funny stuff, right? They can lose writes, they can damage the writes as they are happening. They can forget some of the data because, you know, on the spinning drives, the heads may touch the surface, which is like pretty bad. You can have similar issues with SSDs, obviously without this, you know, without the heads. We also have issues with magnetic storage in case of like power surges and so on. High temperatures. Sometimes people claim the storage was, you know, damaged by like a cosmic ray or something. I will get to that in a minute. But this is pretty common case, like what used to be the problem, right? On software level, we have bugs, right? I mean, like, or incorrectly handled corner cases or whatever. Typically, it could be in, say, operating system, in like a bug in the file system code, or in the kernel memory management or something like that. I will have an example about that either. And obviously, we have bugs in Postgres itself, right? I mean, like, it's like more than 1 million rows of code. And even if we have like a lot of tests, we are very careful about correctness, and we do our best to actually keep your data safe. Once in a while, we have bugs, right? So that's why it's important to keep your database up to date. And finally, if you are a DBA, you have probably done a mistake in the past, right? You have dropped the wrong table. Maybe you were running out of space, so you have removed transaction logs by mistakes because for some reason it was called PGX log. So obviously that's just logs, right? You can just remove that. Don't do that, please, right? Maybe you have done something else which resulted in like data corruption. despite the database documentation telling you like, no, this is not safe, maybe you have done that. I will kind of ignore the last bit because that's really difficult to protect against, right? I mean, like, people will do mistakes no matter what. So I will talk mostly about the first couple of sections. One thing I'd like to mention here is that data corruption is very rare. I mean, like, it's something that is not happening every day. If you have an environment where every day you get a corrupted database, you need to fix your environment, right? That's really bad sign. But even if it's a very rare event, it's typically like a one-off, right? So one day you will get a data corruption because of storage issues. The next data corruption issue will probably be caused by something very different, right? It might be a bug in the database or something. So that's what this means is it's very difficult to give you, a recipe for solving data corruption because each case is very different. Each case will affect different part of the database, and it's very difficult to give you a unified set of steps addressing all of those, right? If I had one, I would give it to you, but I don't, right? So it's usually like ad hoc investigation, ad hoc fixes. I have said that one of the environment causes for data corruption are cosmic rays, right? I mean, like, you are running a database on a system which has, say, RAM, and a charged particle from the space came and flipped a bit, right? I'm not saying it's not happening. I'm saying that whenever someone is telling you, like, this is the root cause, they are probably bullshitting you, right? It just means, like, they don't know what's the reason, so they are blaming the thing that they are not responsible for, right? And I've done that before, so this is one of the, I do admit doing that. And I will get to that in a minute when talking about network attached storage. So about the storage data corruption, like, this used to be very common, especially in the past. Postgres was one of the cheaper databases, right? People were running there because it was a way to save money on licenses, and that's still true. But people were also saving on hardware, so they've been running that on shitty disks, on like low-end servers and whatever. So there were issues with disks not having properly backed up caches and losing writes, and in case of power outages and so on. Cheaper RAID controllers had the same issue with write caches and so on. But we have kind of learned the lesson, and we know that that reliable hardware is the key here, right? So you need to get good hardware which actually provides the guarantees in case of data power loss or crashes or random reboots or whatever. So it got really better over time, right? So when you now buy a mid-range or low-end database server, it's probably safe from this standpoint, right? The disks are good, people learned how to monitor stuff, and the quality of the hardware is generally quite good. Obviously, people are now running a lot of cloud instances, right? Like the likelihood that you are running your database on-premise is quite low, right? You are probably using something like Amazon, Azure, whatever. So, and the things actually got worse again, right? First of all, the network attached storage is kind of, it has very different profile of failures, right? I mean, like, it fails in different ways. It has different issues. You need to monitor it differently. There are layers of virtualization everywhere, so which is good from the standpoint that you are kind of isolated from the outside, but it's also bad because you are. It makes it impossible to investigate over the boundary, right? So this is kind of annoying because we are seeing storage level data corruption issues more often again. That's especially true for like enterprise SAN appliances, which sometimes do like funky stuff under the hood. So for example, you start like migrating volumes or whatever, and data get mixed up or something, right? Right. So that's storage corruption. I will give you some advices on how to actually configure and pick hardware at the end. So software issues, that's kind of more interesting for me as a developer because that's something I can affect, right? I mean, like that's something I can fix either in the kernel or in Postgres itself. The truth is that when it comes to the operating system, Postgres is kind of gullible. It's trusting the operating system to do the right thing, right? Postgres is not using direct I/O as some other databases. Postgres is relying on the page cache, right? So whenever Postgres writes stuff into the data files, it will just hand it over to the operating system and say, well, write it out. And it kind of assumes that this works fine. But nothing is perfect. There are kernel bugs, there are file system bugs, there are glibc bugs, or things you could see as bugs. So one of the examples of software level issues in Postgres is collations. Who knows what's a collation, by the way? Right, so like 10 people. Well, collations are rules for sorting text according to language-specific rules, right? So for example, we have collations for Czech. There are collations for different types of English. There are collations for Chinese or whatever. Each language has a specific set of rules which changes over time, right? So once in a while, you will get slightly more precise rules for Czech language, for example, right? And whenever that happens, that kind of breaks indexes in Postgres, right? Because if you have indexes on a Czech names, for example, those do follow the rules for Czech language. And indexes in general are based on ordering of the values, right? It's not like a simple list, it's a tree, but it's based on ordering. And when this ordering changes, the index is suddenly invalid, right? So where does Postgres actually get those rules? Well, historically, Postgres was using that, the version provided by glibc, at least on Linux. Other operating systems have similar libraries. But the truth is, glibc is kind of shitty when it comes to versioning. I mean, like, they do version the glibc itself, but they don't version the collations properly, right? And what we don't want to do is, whenever a glibc version upgrades, we don't want to invalidate all indexes, right? That would be insane because, I mean, you could get like 10 different versions of glibc before the given collation that you are using actually changes, right? That's quite a rare event. But when it happens, it's kind of damaging for the database, right? So we don't really know how to do that. With glibc, we leave that up to the user, which is like, we don't know how to do that. So we leave that up to the user. He doesn't know how to do that either, but it's not our business, right? So it's kind of like non-solution, to be honest. But the truth is, this actually affects other cases, it's not just about updating the glibc, right? For example, if you have two different machines, like running different versions of Red Hat, for example, those are likely running different versions of glibc. And if you set up a streaming replication like master standby between those, suddenly the standby will be broken, right? Because it will get all the data, all the binary changes from the primary, but that's not how it works on the standby, right? Because it has maybe a different location, locale, right? So that's kind of annoying. The only solution to that is ICU, which is like a standalone library. It's a different source of collations than glibc. So if you are running or will be running Postgres 12, you should be, or Postgres 11, where this was actually introduced. This is probably something you should configure and use. The other and probably more serious issue, I mean, like the collations and the indexes broken, that's fairly simple to fix, right? I mean, like, because it only affects the secondary storage, which is indexes, right? And you can reindex without losing any user data. So maybe you will need to fix some, duplicate values or something which was not detected originally, but you kind of don't lose data. It's easy to restore from or recover. But the other issue that we have suffered like 2 years ago is called fsync gate. Anyone heard about that? Well, so let me scare you a bit. So Postgres, as I said, relies heavily on the operating system to write the data to disk, right? So whenever we do a commit, we flush the transaction log. We do fsync on it, right? It's a file, a sequential file that we write into and sync once in a while. So that's okay, that works, no problem there. Then we have a checkpoint which allows us to remove the old parts of the transaction log, which means once in a while, we also write from the all the modified data from the database cache to disk, right? Because those changes were described in the transaction log, which provides us protection against crashes or whatever. But once in a while, we need to flush this from the database cache to disk to remove the old version of all parts of the transaction log and continue. Now, what happens when the fsync fails? I mean, like, the storage may become temporarily unavailable when it's, for example, network-attached storage or something. So what happens when the fsync returns error, right? Fsync is like a syscall, right? Well, the idea was like, well, we can just retry, right? I mean, like, the data is still in the page cache, so we can try again, and only when it actually succeeds, we will remove the old version of the transaction log, and we will continue, and we will not lose any data. We might accumulate large amounts of transaction log, but that's okay. This assumes two things. First, it assumes that we actually get the message about failed fsync, which is not quite true. And it also assumes that the operating system still has the memory, still has the modified data in memory. And the truth is, well, it works like this, right? Postgres has the modified data in shared buffers, which is like the database managed memory shared by all processes. Then when we do a checkpoint, we write that into page cache. At the end of the checkpoint, we do fsync, which forces it to disk, right? And we kind of assume that we can do this and then repeat this part writing to the disk. But the truth is, it's not true, right? I mean, like, different versions of Linux kernel were kind of broken in different ways. So we never actually get the message about the fsync in different cases. Which means we don't even retry in those cases, right? We just lose the data, and that's kind of sad. So this was actually fixed in fairly new kernel, like 4.13 or something. The other part is when the fsync fails, the operating system actually just removes the data from the page cache anyway, and expects the application to kind of write that data again, right? But at that point, we don't actually have that in the shared buffer anyway, so we kind of lose the data entirely. And obviously, when we've been fixing this, because we had to rework how actually Postgres responds to the error from fsync, we run into a bunch of issues in actually in the Postgres code, which kind of illustrates the fact that error reporting or error handling is one of the least tested parts of any code base. So I have already mentioned that cosmic rays are kind of like, I don't know, right? And the truth is, NFS, or network attached storage, is a similar thing. Because we've been blaming NFS for data corruption for years, but the truth is it was actually affected by these fsync issues because just the network storage was having these issues due to like intermittent network failures or something. Right. So you could also have a data corruption at database level. It could be, bogus data, violated constraints, or whatever. Those are typically caused by, storage level data corruption issues. We had like pretty bad cases of data loss due to handling of transaction state. Those should all be currently fixed. Like, we don't have any live data corruption issues that we are aware of. And you should actually see, this is one of the reasons why you should update the database when we release a new version, right? Because the minor versions, they may not be adding new features, but they are definitely fixing data corruption issues once in a while. Okay, pilot error, I will skip that. So what can you do about that? Well, first, you need to use good hardware. I mean, like, you may need to pay a bit more for that, but it's definitely worth that because eventually you will pay that in like developer and DBA time anyway, right? If you buy shitty hardware, you will have to solve issues eventually. And update regularly. That's what I just mentioned a minute ago. You need also to test the hardware, right? I mean, like, sometimes you will get hardware configured in strange ways. Sometimes the hardware is just lying to you about like fsync speed or whatever. That essentially, especially true for like virtualized machines where you don't actually see into the host. So the only way to actually assess the reliability is by measuring the speed, right? There are some physical limits, like how many fseeks or fsyncs can a given hardware do. So be careful about like unexpectedly high performance of that. Make sure you have backups. I mean, like I said that for data corruption issues, there is no universal solution like recovery steps. The truth is, the only reliable thing is backups, if you have them. So please do. Maybe keep the backups for a bit longer, because sometimes it takes like a longer time to actually discover that you have data corruption. So you may need to go like a month back. The worst cases of data corruption are in like old parts of the database, right? It's a database like data that you haven't touched for a year, and then after a year, when you need to actually read them, you realize actually there is a data corruption. So the only solution to that is actually run some workload that actually checks the data, reads the data from disk, and makes sure that actually it's correct. So one solution to that is like verify checksums, which is a tool available with Postgres. The other option is a pgdump, which is a logical backup solution. You probably don't want to do that, use that for actual backup and recovery, but it's one of the tools that actually has to read all the data from tables and output that to a text file. You will just run that in, redirect it to devnulls because you don't want the data, because the recovery would take ages. But it's a useful way to actually read the database as a whole. Fixing data corruption, as I said, is like impossible. Just restore from backup. That's like, if you really need to do ad hoc fixes, like fixing the database in place, be very careful. You probably need help from someone like me or like a professional database developer. Well, there's a very good talk by Christophe Paris, who is working for a different company, and he actually gives you examples about different cases of data corruption and how actually they recovered from that, right? So that was like from 2017, but it's still valid. So I have like a minute about data checksums, if that's okay. No, okay. So I will skip that. And any questions? Right. Okay.
Which is, logs are important for you or not really?
Logs?
Logs.
Okay, so the question is whether logs are important for me or not. Well, it depends. I mean, like the server log, which is like a list of messages from, server processes or whatever, not really. I mean, like that's something I would, when you run out of disk space, that's probably okay to delete or so on. I don't know in what sense important. What I was mentioning is that we also have another type of log, which is called transaction log, which is the primary protection of the database. And what used to be pretty common is that people run out of disk space. They've been looking for things to delete. The transaction log can be like pretty large, like tens of gigabytes. And unfortunately, it was stored in a directory which has a log in the name. So they were like, oh, there is a lot of logs here. I don't need those, and remove that, right? And at that point, it's like, a sad kitty meme. It's like, yeah, I mean, like, sorry, your database is corrupted, and there is no way to recover that. I mean, like, so I'm not sure if that answers the question, but the server log with messages, what the database was doing, describing that, which you can actually see, and with like slow queries and whatever, that's not important for the database. That's important for the people investigating what happened. The server log, the transaction log is important. Okay, any other questions?
Anybody?
Right?
We have one more. What about the checksums? Do we want to use them?
Right, so let me skip here. So checksums, what are checksums? When Postgres writes data from, I don't see that. When Postgres writes data from the shared buffers into the operating system, checksums are like a small checksum of the 8 kilobyte page, right? So we know whether the page was damaged or corrupted outside Postgres, like by operating system or something. The truth is, so it will protect you against some cases of data corruption. When, for example, someone goes and modifies like a single byte or whatever in the data file, or it gets corrupted during a backup or something. So it's a useful protection against that, but it also has a bunch of disadvantages. It's not a complete solution. There are definitely cases of data corruption this can't actually catch. like for example, when the corruption happens in shared buffers. I mean, like that happens before the checksum is computed and updated in the page. We can't detect that, right? So like buffer overflows or whatever, which can happen in Postgres because it's written in C, so it's kind of unsafe in this sense. That can happen. It can't, for example, detect cases when we just lose the whole page right? Because then we have like obsolete page with the correct checksum, we can't actually detect that. It's useful. I mean, like you can enable that, you can check that. We kind of do recommend that to deployments where the data corruption is more important than immediate availability for the users, right? Because what this means, when you don't have the checksums, the users are still able to access the page, access the data, even if the page is corrupted, but they, for example, can't access the single record, single row on the page, but they can select the rest, right? So only people accessing the single corrupted record will get an error. For everyone else, it will work. With checksums, suddenly everyone who even tries to access the page will get an error. So it's like a trade-off between correctness and availability. And the other problem with checksums is it's just a detection of the data corruption. It will give you an error, but it will not tell you how it happened. It will not tell you how to recover from that. It will not tell you what you need to do, right? So those are like, I like data checksums, but I also see like this as a drawback. So it's difficult for me to give you like, yeah, always use them, right? Like, yeah.
Thank you very much. We are out of time for the next questions. If you'd like, please catch Tomáš.
Yep.